Welcome to lecture 38. We are talking about temperature measuring instruments. In your previous lecture, we have talked about thermocouples, which are based on thermoelectric principles. Today, we will talk about a temperature measuring instrument based on variation of resistance with temperature. So, we have talked about thermal expansion methods, we have talked about thermoelectric sensors, and now today we will talk about electrical resistance sensors. Under electrical resistance sensors, we will talk about resistance temperature detectors or resistance temperature device, commonly known as RTD, and thermistors. So, today we will talk about resistance temperature device or resistance temperature detector or RTD. So, what you see is some images of RTD and thermistors. Now, the basic principles on which these electrical resistance sensors work are as follows. The electrical resistance of many materials change with temperature in a reproducible manner. The change in resistance can be measured easily by a bridge circuit and thus can be related to temperature. So, the variation of electrical resistance with temperature is reproducible for many materials. So, if we can measure the change in resistance due to change in temperature using say a Wheatstone bridge principle, we can relate the change in resistance to change in temperature. Two types of materials are commonly used: conductor metals and semiconductors. The sensors made from conductors or metals known as RTD or resistance temperature device, and sensors made from semiconductor materials are known as thermistors. On the left, what you see is typical variation of resistance with respect to temperature for certain materials such as nickel, copper, platinum and tungsten. They are all metals and RTDs are made of these metals. So, they are common metals for making RTDs. You can see that there is a region over which the relationship between temperature and resistance is linear. Or approximately linear. Let us call this principle. So, both RTD and thermistors are based on the same principle, which is variation of electrical resistance with change in temperature. And we see that for some metals such as nickel, copper, platinum, tungsten, the variation is to some extent linear with respect to temperature, and they are good candidates for making RTDs. So, the resistance of a metallic resistance element changes with temperature in a specific manner. Therefore, the temperature can be measured by measuring the change in resistance of the element. The resistance measurement may be performed by a bridge circuit, Wheatstone bridge principle. So, this is a typical equation which has been used for relating resistance of a metal at temperature T with temperature. So, R equal to R 0 into 1 plus alpha 1 t plus alpha 2 t square, it can go up to alpha n t to the power n, where R is resistance at temperature T expressed in ohm, R 0 is the resistance at reference temperature T 0 expressed in ohm, and alpha are experimentally determined constants. Now, if I apply this equation in a narrow range, I can retain only the terms which are first order in T and neglect all second order and higher order terms. So, in that case, the resistance may be expressed as R equal to R 0 into 1 plus alpha t, which shows a linear relationship with respect to temperature. If you retain up to second order term, it will be R equal to R 0 into 1 plus alpha t plus beta t square, and then you will have a slightly nonlinear equation. The equation where R equal to R 0 plus 1 plus alpha t, we call this alpha as temperature coefficient of resistance and expressed as ohm per ohm degree Celsius. Alpha is positive for metals. So, this is typically how a RTD will look like, a commercially available RTD will look like. I will show you a real RTD today. So, the resistance temperature device may be a metal film deposited on a former or a wear wound resistor. So, it is basically the resistance temperature device or RTD is basically an electrical resistance wear. It may be a resistance wear or it may be a thin metallic film. So, if it is a thin metallic film, it is deposited on a former, and if you consider a resistance wear to be RTD, it will be wound on some support, let us say a ceramic bobbin support, and the change in resistance of this thin metallic film or the wear will be considered as measurement for the temperature. So, the RTD, which may be a metallic film deposited on a former or a wear wound resistor, is sealed in a glass ceramic composite material. The electrical resistance of pure metals is positive and it increases linearly with temperature. Change in resistance can be easily measured by a Wheatstone bridge principle. So, inside this you have the resistance wear or the thin metallic film, which will work as a resistance thin film, and the extension leads will come out here and this will go to one arm of the Wheatstone bridge. So, you can establish first the null point and then can expose this to the medium whose temperature you are measuring. Due to change in resistance, there will be an unbalance in the bridge and accordingly you can measure the change in resistance, and that can be related to the temperature. These devices have high accuracy and can be used to measure temperatures from -200 to 1000 degrees Celsius, although commonly it is used up to 700 or 750 degrees Celsius. Now, by measuring the resistance of the RTD element, one can determine the process temperature if the change in total resistance measured is affected only by the process temperature. So, this is my RTD, which is basically one arm of this Wheatstone bridge, and this is the voltmeter. Now, when I want to measure the temperature of a medium using this RTD, I will expect that the change in resistance of the RTD element should happen only due to change in temperature. But the resistance element, which is wire or a thin metallic film, will be connected to this Wheatstone bridge. It will be connected to this readout element voltmeter by extension leads. So, in actual practice, the RTD element is connected by wires to the readout instrument or voltmeters, and the resistance of the leads will introduce an error in the measurement. So, you have to compensate for that error. Let us look at this bridge circuit again. You have this RTD element which is connected to the Wheatstone bridge using wire A and wire B. So, these are lead wires or extension leads of RTD element. Now, the length of the wire from the RTD to the Wheatstone bridge circuit may be significant. If this is significant, it will add up resistance. So, the change in resistance will happen not only due to change in temperature as indicated by RTD, there is additional resistance of wire A and wire B. Since the device has relatively low resistance, the lead resistance of RTD assembly can add a significant error to the measured resistance. What is shown here is known as two-wire connection. So, the RTD element is connected to one arm of the Wheatstone bridge using two extension leads or two wires. So, this is known as two-wire connection. So, in these two-wire connections, the resistance of both the wires will add up. Let us say I am using copper wire to connect RTD to one arm of Wheatstone bridge, and let us say, for example, the copper wire's resistance is expressed as 0.105 ohm per feet, and let us say I am using 100 feet long wire. because the Wheatstone bridge may be 100 feet away from the point of measurement where the RTD element will be inserted to the medium. So, each lead wire will add 100 into 0.105 ohm, which is 10.5 ohm per lead wire. So, two extension leads together will add 21 ohm. So, this may be substantial to increase the error to a significant extent. So, as a compensation for this, we use 3-wire connection. So, we take an additional wire which works as a compensation for this lead wire's resistance. So, if you look at the schematic, this is the RTD element connected to Wheatstone bridge using wire A and wire B. Now, these two leads to the sensor are on the adjoining arms. If wires A and B are of equal length, in other words, if wires A and B have same resistance, their impedance effects will cancel each other. The third wire C acts as a sense lead and has same resistance as A and B. So, if you write down the conditions for balance, you will now see that the effect of lead resistance A and B are getting cancelled out. So, commonly RTD elements will have 3-wire connections as shown in the schematic. Note that this is that readout or the voltmeter of the Wheatstone bridge, to which the wire C is connected. There is another connection known as 4-wire connection for RTD. The 4-wire technique does not use the Wheatstone bridge method of measuring the resistance of an RTD. 4-wire technique uses a current source along with a remotely located digital voltmeter. So, this is the resistance element, this is the current source and this is the digital voltmeter. The output voltage read by the digital voltmeter is directly proportional to RTD resistance. So, the output voltage read by the digital voltmeter is directly proportional to the resistance of the RTD element. The 3 bridge resistors are replaced by one RTD here. The digital voltmeter measures only the voltage drop across RTD. So, this voltmeter measures the voltage drop across RTD and is insensitive to the length of the lead wires. So, this 4-wire connection leads to improved accuracy. For construction of RTDs, there are two common methods: winding of platinum wire on a glass or ceramic bobbin followed by sealing with molten glass, or depositing a platinum or metal glass sari on a ceramic substrate. The film is then etched and sealed to form the resistance element. This is called thin film sensor. So, you can have winding of say platinum wire on a glass or ceramic bobbin followed by sealing with molten glass. So, this is the ceramic body and platinum winding is shown. So, this is put within a protective tube, and what you see is that two extension leads are coming out. So, two extension leads will come out for 2-wire connections. You will see 3 extension leads coming out for 3-wire connections. So, the platinum winding is enclosed in a ceramic body. So, this is another schematic. You have the platinum wire which is wound around the ceramic bobbin and then put inside a protective casing. So, the platinum leads are here and they will be connected to the Wheatstone bridge for measurement of change in resistance, which will be related to temperature. So, this is a schematic representation of thin film sensor. Again it shows the wire wound around a ceramic or glass bobbin and there is a protective encapsulation around it. So, the difference between these two is one is wire, another is thin film. Both work as resistor element. A very common RTD is PT100 or platinum 100. PT stands for platinum. So, you will very commonly find in laboratories or in industries an RTD known as PT100. So, platinum thermometer are made in two forms as discussed previously, as a coil wound on a ceramic bobbin or as a film deposited on a ceramic substrate. The nominal resistance at 0 degree Celsius is typically 100 and that is why it is called platinum 100. So, PT100 means this is a RTD made of platinum and the nominal resistance of this platinum RTD is 0 degree Celsius at is 100 ohm at 0 degree Celsius. So, the nominal resistance at 0 degree Celsius is typically 100 ohm. Such RTDs are called PT100. So, PT stands for material of construction platinum and 100 stands for the fact that the nominal resistance of this RTD is 100 ohm at 0 degree Celsius. Also 1000 ohm versions are also available. That means the nominal resistance at 0 degree Celsius will be 1000 ohm, but typically the nominal resistance is 100 ohm and we call these resistors or we call these RTDs as PT100. The sensitivity for PT100 is 0.385 per degree Celsius and 3.85 per degree Celsius for 1000 ohm type. A high resistance gives higher measurement sensitivity and the resistance of connecting leads has less effect on measuring accuracy. Note that if the resistance of the resistance element is low, then the effect of the lead wire's resistance will be significant. But if the resistance of the resistance element is very high, then the lead wire's resistance will have relatively a less significant effect. However, when you go for high resistance RTD or platinum RTD, the cost goes up. One test for PT100 RTD you can perform in laboratory is you take the RTD, the image shows that it is a 3-wire connection and 3 wires are coming out. So, you dip this RTD in a beaker where you have ice and water mixture. So, ice water mixture will have 0 degree Celsius temperature. So, when equilibrium is established, if you measure the resistance, you will see the resistance is approximately 100 ohm. So, you will know that your PT100 is working properly. The selection of RTD materials is governed by high temperature coefficient. If you have high temperature coefficient, there will be improved sensitivity, high resistivity of the material for larger output, linearity of resistance temperature relationship. This makes the calibration very convenient. Stability of electrical characteristics for repeatability, good mechanical strength and resistance to contamination. So, when we select RTD materials, we will choose materials with high temperature coefficient, high resistivity of the material which shows linear relationship between resistance and temperature, which has stable electrical characteristics, which has good mechanical strength and which is resistant to contamination. Here we present some materials which are commonly used for making RTD such as copper, nickel, platinum and tungsten. Their ranges are also given. Copper can be used between -200 to 250, nickel -100 to 350 degree Celsius, platinum -250 to 700 degree Celsius and tungsten -270 to 1100 degree Celsius. The temperature resistance coefficients are also given. Now, apart from lead wire error or lead wire resistance error, there is another source of error in RTD. This is known as self-heating. When you want to measure temperature using RTD, you have to feed a current through it, and that will cause I square R heating in the device. With a change of current, the reading may change because of the heating, because if it is heated, if RTD is heated, its resistance will change. In still air, the error due to self-heating is about 0.5 degrees Celsius per milliwatt. One possibility to minimize the error is to immerse the resistance in a high thermal conductivity fluid, so that the heat is immediately dissipated. So, we will stop our discussion on RTD here.